Bismillahirrahmanirrahim. Welcome to my YouTube channel Calculus and Mathematics Learning. In the previous video, I started and commenced with exercise number 8.2 relevant with chapter number 8, relevant with the topic Eigen Value, Eigen Vector and Diagonalization. So in the previous video, I solved some of the questions in exercise number 8.2. So in today's video, I will solve some of the questions. So let's move toward question number 9 of exercise 8.2 lecture 11 BS linear algebra by Bernold, Kolman and David Arif 8th edition. Chapter name is Eigen Value, Eigen Vector and Diagonalization. So in the previous video we solved 8 questions. So today we will start from question number 9. It tells that find a 2 cross 2 non-diagonal matrix whose eigen values are 2, minus 3 and associated eigen vectors are minus 1, 2 and 1, 1 respectively. Move to solution. Let A be the desired 2 cross 2 non-diagonal matrix. Since eigen values are distinct, eigen value are given which is 2, minus 3. These are distinct and different. So it means that A is diagonalized according to the theorem. A is diagonalized matrix and therefore it exists a non-singular matrix. So let's suppose this minus 1, 2, 1, 1 is a matrix P. So such that we have the condition P inverse into A into P is equal to B. Now over here B is a diagonal matrix whose diagonal entries are lambda 1, lambda 2, which is actually our eigen value 2 minus 3 of A. So over here 2 minus 3 is the eigen value and the non-diagonal entries should be 0. So this is our B matrix. Now finding P inverse from this matrix using determinant 1 over determinant of A. So the determinant of this matrix is minus 3, 1 over minus 3 and adjoint is this of this matrix. By simplification it gives us P inverse minus 1 by 3, 1 by 3, 2 by 3, 1 by 3. Now from over here shift P inverse on the right hand side it become AP is equal to PB. Now shift this P on the right hand side it become A is equal to P inverse into B into P. P inverse is given, my B is given and my P is given. By multiplying these three matrices and by doing simplification it will give us the required 2 cross 2 non-diagonal matrix minus 4 by 3, minus 5 by 3, minus 10 by 3 and 1 by 3. Now move to the next question, question number 10. Find a 3 cross 3 non-diagonal matrix whose eigen values are minus 2, minus 2, 3 and associated eigen vector are 1, 0, 1, 0, 1, 1 and 1, 1, 1. Move to solution. Let desired matrix which is a non-diagonal is A. So my P will be 1, 0, 1, 0, 1, 1 and 1, 1, 1. This is my P. And my B will be actually on the diagonal. This eigen value, lambda value will lies minus 2, minus 2 and 3 and the non-diagonal entries should be 0. Now over here I find the inverse of this 3 cross 3 non-diagonal matrix using row echelon form. P partition identity matrix. This is P and this is identity matrix. So on the left hand side in the result identity matrix will be generated and on the right hand side the inverse will be generated by using some row echelon form, by using some reduction, by using some operation. So it gives P inverse is equal to 0 minus 1 1 minus 1 0 1 1 1 minus 1. Now using the formula P inverse AP is equal to B, shift P inverse on the right hand side it become BP, shift P on the right hand side will become A is equal to P inverse BP. Now my P inverse is given, this is P inverse. Now my B is also given, this is B and my P is also given. By multiplying these three matrices and by doing simplification it will give us my required 3 cross 3 non-diagonal matrix 3 pi 3 pi minus pi and minus 7. Now that has that from question number 11 to 22. Find a possible non-singular matrix P such that P inverse AP is diagonal. Move toward 11 question. 4 2 3 2 1 2 minus 1 minus 2 0 given. We use characteristic polynomial definition. F of lambda is equal to determinant into lambda into identity matrix minus given matrix. Now by simplification it will give us this matrix. Now here we have determinant. So take the determinant, expand with R1 this determinant, it will give us lambda f of lambda is equal to lambda minus 1 into lambda square minus 4 lambda plus 3. From here we get three values 1 1 3. So from over here the eigen values are repeated. So the theorem is palo. So we move to the next theorem. Ax is equal to lambda x. So lambda x minus x is equal to 0. Take x common, we left with lambda I3 minus a. Now put lambda 1 over here, so it become I3 minus a. Now by simplification it will give us just one value of eigen vector x is equal to minus r0 r. Now by putting lambda 3 over here in this equation it will give us another eigen vector. So 2 eigen vector is generated. Remember the given matrix is 3 cross 3 order matrix. We need 3 eigen vector, not 2 eigen vector. So this theorem also fails. It means the given matrix is non-diagonalizable. So we are not able to find a non-singular matrix P. Now move to the next question, question number 12. 1 1 2 0 1 0 0 1 3. Using definition f of lambda is equal to determinant into lambda into identity matrix will give us this minus time of the given matrix. So by simplification it will give us this matrix. Now expand with column 1. So lambda minus 1, this will give us 0. So for lambda minus 1 cross this first column and this row, we left with lambda minus 1 into lambda minus 3 and this will give us 0. So from over here 3 solution will be generated for the eigen value lambda is equal to 1 1 3. Now over here solution is repeated, it means the theorem is failed. Move to the another theorem, x is equal to lambda x. So take x common, we left with lambda into I3 minus a. Now put lambda 1 over here, and by simplification it will give us 2 eigenvector, because over here 2 variables is created. Let's suppose from over here minus y minus 2z is equal to 0, and from over here minus y minus 2z is equal to 0, but we don't have any value of x and z. So let z is equal to arbitrary constant r, and let x is equal to arbitrary constant t. So because of these two values t and r over here, let's suppose t is 1 0 and r is 1. Let's suppose t is 1, r is 0, so it will give us 2 eigenvector. By putting 3, it will give us another eigenvector. So 3 linearly independent eigenvector is generated. Because the given matrix is 3 cross 3 order matrix, we need 3 eigenvectors. So 3 eigenvector is generated. It means the given matrix is diagonalizable according to the theorem, and the given matrix P will be the first eigenvector 1 0 0, the second eigenvector 0 minus 2 1, and the third eigenvector 1 0 and 1. Now move to the next question, question number 13, 1 2 3 0 1 0 2 1 2. So f of lambda is equal to determinant into lambda into identity matrix will give us this matrix minus original matrix. So by simplification it will give us this matrix. Now determinant, so by determinant I expand this with r1. So by simplification it will give us lambda minus 1, lambda plus 1, lambda minus 4. So from over here 3 eigenvalues are generated, minus 1 1 4. So using definition x into lambda I3 minus a. So put lambda minus 1 over here, and a is this matrix. So by simplification it will give us 2 eigenvector s1 and x2. Now further, by putting 1 in this formula it will give us another eigenvector, and by putting 4 in this formula it will give us another eigenvector. So from over here 4 different type of eigenvector is generated. But remember over here the given matrix is 3 cross 3 order matrix, we need 3 eigenvector, not 4 eigenvector. It means that this theorem fails and the given matrix is non-diagonalizable. So because of non-diagonalizability we cannot find a non-singular matrix P. Now move to the next question, question number 14, 0 minus 1 2 3. So f of lambda is equal to determinant into lambda into identity will gives us this minus original matrix. By simplification it gives us this matrix. Now taking the determinant, so lambda into lambda minus 3 gives us lambda square minus 3 lambda, and minus into minus gives us plus 2. So from over here lambda is equal to 1 into 2 eigenvector is generated. So using equation ax1 is equal to lambda 1 xo. So x1 into lambda 1 I2 minus a. So lambda 1, let's suppose put 1 over here. So 1 into I2 minus a into x1 is xy is equal to 0. So it gives us this matrix. Now using row echelon form over here it gives us 1 1 0 0 into xy. So let x plus y is equal to 0, and let's suppose I consider y is equal to r, so x is negative r. So it gives us x1 is equal to xy minus r, and r, let's suppose r is 1, it gives us minus 1, and 1 plus eigenvector is generated. Using x2 into lambda 2 I2 minus a. So lambda 2 is 2. So 2 I2 minus a. A is given, I2 is also given. So 2 I2 minus a will give us this matrix using again reduction row echelon. So it gives us 2 1 0 0. So by elimination we get 2x plus y is equal to 0, and let's suppose I consider y is equal to r. So it gives us x is minus r by 2. Let I consider r is 2. So it gives us minus 2 by 2 gives us minus 1, and y is, let's suppose, 2, because r is I consider 2. So over here eigenvector x2 is generated, x and y. X is minus 1 and y is 2. So it means the non-singular diagonal matrix is x1 minus 1 1 and x2 is minus 1 2. This is the required non-singular matrix. Now move to the next question, question number 15, 8 1 0 0 8 0 8 0 0. So f of lambda is equal to determinant into lambda into identity matrix will give us this matrix minus original matrix. So by simplification it will give us this matrix. Now over here we have determinant. So taking the determinant expanding with the column 3. So over here this and this will give us 0. So I left with this lambda. So for lambda cross this row and this column, because in this row and column this lambda lie. So we left with lambda minus 8 minus 1 0 lambda minus 8. Taking the determinant gives us lambda minus 8 whole square, and this gives us 0. From over here f of lambda is equal to 0, so we get lambda 0, and for f of lambda is equal to 0 we get lambda is equal to 8 and 8. So eigenvalue are repeated, so theorem fail, and proceed to the next theorem. Lambda x minus x is equal to 0. Take x common, we left with lambda I3 minus a. So first put lambda 0 over here, it gives us minus a time of x. So by simplification it will give us just one eigenvector x1 0 0 1. Now by putting lambda is equal to 8 in this equation, so it will give us just one eigenvector. So over here 2 eigenvector are total generated, but remember over here the given matrix is 3 cross 3 order matrix. So it means that we need 3 eigenvector, different type of eigenvector. So over here because of 2 eigenvector generated, it means the given matrix is non-diagonalizable according to the theorem. So it means that we are not able to find a non-singular matrix P. Now move to the next question, question number 16. Question number 16, 3 0 0 1 3 1 0 0 1. So f of lambda is equal to determinant into lambda I3 minus a. So lambda multiply I3 will give us this minus a is original matrix. By simplification it gives us this matrix. Now expand with R1. So these two entries will give me 0 and I left with lambda minus 3. So for lambda minus 3 cross this row and this column, we left with lambda minus 3 minus 1 0 lambda minus 1. Taking the determinant, it gives us lambda minus 3 into lambda minus 1 and this gives us 0. From over here I get three values, lambda 3 and lambda 1. Now over here eigen value lambda value or eigen value are repeated, so it means the theorem failed. Proceed to the next theorem, lambda x minus x is equal to 0. Take x common, we left with lambda I3 minus a. First put lambda 1 over here and by doing simplification it will give us just one eigen vector x1 is equal to 0 minus 1 2. Now over here 3 is repeated, so we will take 1 3. So for lambda is equal to 3 it becomes 3i3 minus a. So this is 3i3 minus a into xyz is equal to 0. By simplification it will give us another eigen vector x2 is equal to 0 1 0. But remember, given matrix is 3 cross 3 order matrix, so we need 3 eigen vector, not 2 eigen vector. It means this matrix is non-diagonalizable and we are not able to find a non-singular matrix P. Now move to the next question, question number 17. 3 minus 2 1 0 2 0 0 0 0. So f of lambda is equal to determinant into lambda I3 minus a. So lambda into I3 gives us this matrix minus a is original matrix. By simplification it gives us this matrix. Now I expand this with R1 not C1. I expand this with R3, third row, this row. So 0 0 gives us 0. I left with lambda. So for lambda I cross this row and this column, so we left with lambda minus 3 into lambda minus 2 and this gives us 0. From over here we take 3 value, lambda 3, lambda 2 and lambda 0. Eigen values are distant, it means the given matrix is diagonalizable according to the theorem. So it means that matrix the required non-singular matrix is possible. So x is equal to lambda x, so lambda x minus ax, take x common, we left with lambda I3 minus a. So put lambda 0 over here, it gives us first eigen vector x1. Now put lambda 2 over here, so it gives us another eigen vector. Then put lambda 3 over here in the same equation, it will give us another eigen vector x3 is equal to 1 0 0. So the required matrix, non-singular matrix, will be p is equal to x1 x2 x3. x1 is minus 1 0 3, x2 is 2 1 0 and x3 is 1 0 0. This is the required non-singular matrix. Now move to the next question, question number 18. 2 2 2 2 2 2 2 2 2. Find a possible non-singular matrix P. So f of lambda is equal to determinant into lambda into identity minus given matrix. So it gives us this. Now by simplification, by expanding this with R1, it will give us the result f of lambda is equal to lambda cube minus 6 lambda square. So it will give us 3 values of lambda 0 0 6. Values are repeated, it means that this given matrix is non-diagonalizable. So the theorem is failed, it means we will move to another theorem. Ax is equal to lambda x, so lambda x minus ax, so x1 into lambda I3 minus a. First put lambda 0, so it will give us just one eigen vector x1, and then put lambda 6 in the same equation, and by doing simplification it will give us another eigen vector 1 1 1. So 2 eigen vector is generated, it means the given matrix is non-diagonalizable. Because the given matrix is 3 cross 3 order matrix, we need 3 eigen vector, so we are not able to find an singular matrix P. Now move to the next question, question number 19. A low triangular matrix is given 3 0 0 2 3 0 0 0 3. So f of lambda will be determinant into lambda into identity matrix gives us this matrix minus original matrix. By simplification it gives us this matrix. Over here we have determinant, so for determinant I expand this with R10. So for lambda minus 3 I cross this row and this column, I left lambda minus 3 into lambda minus 3 and this gives us 0. So the result is lambda is equal to 3 3 3. Eigen values are repeated, so the theorem fails. Proceed to the next theorem. X is equal to lambda x, so lambda x minus x is equal to 0. X common, we left with lambda I3 minus a. So put lambda 3 over here, become 3 I3 minus a into x. So 3 into I3 gives us this, minus a is given into xy is equal to 0. By simplification it gives us minus 2x is equal to 0, and I don't have any value of y and z. So let's suppose I consider y r and z t. So over here my x is xyz, so x is 0, y is r and z is t. Now over here we have two conditions. For r is equal to 0, t is equal to 1, we get this, and for r is equal to 1, t is equal to 0, we get this. Over here we have 2 eigen vector, not 3 eigen vector. It means the given matrix is not diagonalizable, and we are not able to find an singular matrix P. Because the given matrix is 3 cross 3 order matrix, we need 3 eigen vector, not 2 eigen vector. Now move to the next question, question number 20, 1 0 1 0 1 0 0 1 2. So f of lambda is equal to determinant into lambda I3 minus a. So lambda into I3 gives us this matrix minus a is original matrix. By simplification it gives us this matrix. Now taking the determinant and expand with column 1. So for lambda minus 1, I cross this row and this column. I left with lambda minus 1 into lambda minus 2 and this gives us 0. From over here we get lambda is equal to 1 1 2. Eigenvalues from over here is repeated, so it means the theorem is failed. Proceed to the next theorem. Lx is equal to lambda x, so lambda x minus x is equal to 0. Take x common, we left with lambda I3 minus a. First put lambda 1 over here, it become I3 minus a into x is xyz. By simplification it gives us 1 eigen vector x1. Now then put lambda 2 over here in the same formula, and by doing simplification it will give us another eigen vector x2. So 2 eigen vector is generated, not 3 eigen vector is generated. It means that the given matrix is not possible because this matrix is non-diagonalizable.